Hey Sarah, have you ever wondered how humans first started counting things before we had numbers as we know them today?
Absolutely, Adam. It is fascinating. Imagine being in prehistoric times, trying to keep track of your herd or how many days until the next season. You would need a way to remember quantities, right?
Exactly. And that is where tally marks come in. People would carve notches on bones or sticks to keep count. Every notch represented an item, an animal, or a day. It was simple, but incredibly effective.
I love that idea. It is like the earliest form of a notebook, but nature-made. And it was not just bones. Stones, shells, and even pebbles were used as counting tools. People would move them around or pile them to signify quantities.
Yes, and what is so interesting is that these early methods were the first steps towards abstract thinking. The act of keeping track, of representing numbers in a physical way, laid the groundwork for later systems of numerals.
And it was not uniform either. Different communities probably had their own methods. One tribe might use sticks, another might use small stones, but the underlying concept was the same: find a way to record what you need to remember.
Right. And some of the surviving artifacts, like the Oshangno bone from Africa, show very clever patterns. It is amazing to think people were thinking mathematically so long ago, even without written language.
It really is. Counting was born out of necessity, but it also sparked creativity. It is humbling to think that something as simple as a notch in a bone was the beginning of all our modern mathematics.
Absolutely. The journey from tally-marked complex numbers is a story of human ingenuity, starting with simple marks and moving towards abstraction.
And it reminds us that mathematics is not just about numbers on a page. It began as a practical, human tool, something we use to understand our world.
Exactly, Sarah. And every time we count something today, we are a part of that ancient tradition.
It is incredible to trace our modern habits back to those first marks on bones and stones. A true testament to human curiosity and problem solving.
And that is the beauty of history, right? Even the smallest inventions can ripple through time and shape the way we think today.
Absolutely. Counting started as survival, but it became so much more. It became a story of human thought.
Sarah, have you ever thought about how people in ancient Egypt and Mesopotamia used mathematics in their daily lives?
Oh yes, Adam. It is really fascinating. Back then, math was not just abstract ideas on a page. It was practical. People used arithmetic to measure fields, keep track of trade, and even plan big construction projects.
Exactly. For instance, in Egypt, the Nile River would flood every year. Farmers had to measure their fields to know how much land they had for planting. They used simple arithmetic to calculate areas and divide land among families.
And in Mesopotamia, merchants needed math for trading goods like grain, livestock, and textiles. They would keep records of quantities and transactions, ensuring everyone knew what was owed or delivered.
Right. And it was not just about counting. They developed early systems of measurement. Length, volume, weight. They needed consistency so that fields, containers, and construction materials were all measured accurately.
And speaking of construction, think about the pyramids in Egypt. Building such massive structures required careful planning. Workers had to measure angles, lengths, and volumes. It was mathematics in action, applied to real-world challenges.
Yes, it is incredible. Even without our modern notation or tools, they were able to calculate quantities and organize large projects. Their methods were practical and precise, showing that math was an essential part of society.
I love that. Math was not just for scholars. It was woven into everyday life: farming, trading, building, and even managing resources for the community.
And in Mesopotamia, clay tablets show records of all these activities. They had lists of goods, calculations for trade, and even problems for learning arithmetic. It shows how integral math was to their civilization.
It is amazing to see how early humans applied numbers and measurements to solve practical problems. They laid the groundwork for everything we take for granted today in mathematics.
Absolutely. From field to pyramids, trade to city planning, math was a tool for survival and progress. And that is a story that connects us to them, even thousands of years later.
And it reminds us that mathematics has always been more than numbers. It is a human invention to understand, organize, and shape the world around us.
Sarah, have you ever thought about the way the Greeks changed the way we think about mathematics?
Definitely, Adam. They moved it from being just practical counting and measurement to a more abstract and logical way of thinking.
Exactly. Take Pythagoras, for example. He and his followers were fascinated by patterns, especially in numbers and shapes. They saw that certain relationships always held true, and that was more than coincidence, it was a discovery of underlying order.
And geometry became central to their thinking. They were not just measuring land or building structures, they were exploring shapes, angles, and the relationships between different forms. It was like they were uncovering the hidden rules of the world.
What I find really fascinating is the idea of proof. The Greeks insisted that a mathematical truth had to be demonstrated logically, step by step, not just observed. That was revolutionary. It turned mathematics into a kind of storytelling, where each statement led inevitably to the next.
And it required creativity as well as logic. To prove something, you had to think deeply about the properties of numbers and shapes, imagine possibilities, and then show why only one answer could be correct.
Right. It is that combination of curiosity and rigor that made Greek mathematics so enduring. Concepts discovered over 2,000 years ago still form the basis of what we teach today.
And it is inspiring to think that their fascination with patterns and logical proof began with simple questions. Why do numbers behave this way? Or what makes one shape different from another?
Exactly. They showed that mathematics is not just about solving practical problems. It can also be the way of thinking, a way of exploring ideas and finding universal truths.
And that is why Greek mathematics feels so alive, even today. It is not just formulas or numbers, it is a story of human curiosity, imagination, and discovery.
Absolutely. From Pythagoras to the great geometers, the Greeks taught us that mathematics is a journey of the mind as much as a tool for the world.
And that journey continues with us, as we explore patterns, reason logically, and uncover the beautiful structures hidden in the world around us.
Sarah, today I thought we could talk about Euclid and how he shaped the way we think about geometry.
Oh yes, Adam. Euclid is often called the father of geometry. What makes his work so remarkable is how he organized ideas using axioms and logical reasoning.
Exactly. Axioms are basic statements that are accepted as true without proof. Euclid started with these simple truths and then built everything else step by step, using deductive reasoning.
I love that approach. It is like building a house where each brick is carefully placed. One idea follows naturally from another, and nothing is assumed beyond what is necessary.
Right. And this method created a system that was clear and reliable. Every proposition in his geometry books could be traced back to the fundamental axioms. It gave mathematics a structure that people could trust.
And their impact was enormous. Not just in geometry, but in all of mathematics. Later mathematicians took Euclid's ideas and extended them to new areas, exploring algebra, number theory, and even modern logic.
It is fascinating how a framework of simple statements could influence so much thinking for centuries. Euclid's work became a model of clarity and rigor.
And it shows the power of logical reasoning. By starting with basic truths and reasoning carefully, you can uncover truths far beyond what you might have guessed at the beginning.
Exactly. It is not just about shapes on a page. It is a way of thinking, a method for discovering reliable knowledge.
And that is why Euclid's geometry has lasted so long. It teaches us that mathematics is about precision, logic, and building ideas step by step.
Yes, Sarah. His influence reaches even today, in classrooms, in research, and in the way we approach problems logically.
And it reminds us that sometimes, starting with simple truths and thinking carefully is all you need to unlock deep insights about the world.
Sarah, have you ever heard the story of Archimedes and his famous bath moment?
Of course, Adam. The story where he realized how to measure the volume of an irregular object by observing the water displacement. That was pure genius.
Exactly. He noticed that when he got into the bath, the water level rose. From that simple observation, He understood a principle that could measure the volume of objects no one had a clear method for before.
And it did not stop there. Archimedes applied his curiosity to levers as well. He explored how small force applied in the right way could move huge objects, famously saying he could move the world if he had a place to stand.
That is the beauty of his thinking. He looked at everyday phenomena water, weights, levers and turned them into discoveries that combined practical invention with deep insight.
And what fascinates me most is that some of his work laid the groundwork for ideas that would eventually become calculus. He studied areas, volumes, and rates of change in a way that was centuries ahead of his time.
It is amazing to imagine him sketching these ideas, experimenting with simple machines and water, and slowly uncovering truths about the natural world. His curiosity was relentless.
And it reminds us that invention and discovery often come from observing the world carefully, asking why things happen, and imagining how they could be explained or applied.
Exactly. Archimedes showed that mathematics, physics, and practical ingenuity could work together, creating insights that still inspire engineers and scientists today.
And that storytelling aspect is so engaging. From a bath to a lever to the stars, his mind connected ideas in ways that seem almost magical.
Absolutely. Archimedes was more than a mathematician or inventor. He was a thinker who saw the patterns in the world and showed us the power of observation, imagination, and reasoning.
And it makes you wonder how many simple moments around us today could spark discoveries that change the way we understand the world.
Sarah, I have always been fascinated by the contributions of Indian mathematicians to the world of numbers.
Me too, Adam. One of the most remarkable things they did was develop the concept of zero. Can you imagine a time when people did not have a symbol or even a concept for nothing?
It is hard to imagine. Zero might seem simple to us, but it completely changed the way people could think about numbers and calculations. It allowed for place value, which made arithmetic much more powerful and flexible.
And speaking of place value, that is where the decimal system comes in. Indian mathematicians created a way to represent numbers using 10 symbols in different positions, which made calculations far easier than ever before.
Absolutely. With zero and the decimal system, large numbers could be written compactly, and complex calculations became manageable. It was a revolution in the way people approached mathematics.
And they did not stop there. Early algebra also flourished in India. Mathematicians explored patterns, equations, and methods for solving unknown quantities long before it became common elsewhere.
What strikes me is the practical and theoretical impact. These ideas made trade, astronomy, and engineering far more precise, but they also laid the foundation for abstract thinking in mathematics.
Exactly. Indian mathematicians showed that numbers could represent ideas, not just counts. Zero was not just nothing, it was a tool that opened up entire new ways of reasoning.
And the beauty is that these innovations spread far beyond India, influencing mathematics across the world and eventually shaping modern number systems and algebra.
It is inspiring. Sometimes we forget that something as seemingly simple as zero was once a revolutionary idea, changing how humans could understand and manipulate the world around them.
Truly, Sarah. The work of these mathematicians reminds us that creativity and insight can transform even the most fundamental concepts into tools that change history.
And it encourages us to look at our everyday tools and ideas with curiosity. Who knows which simple concept today might transform the world tomorrow.
Sarah, have you ever explored the mathematics of ancient China?
Yes, Adam, and it is fascinating. The Chinese developed some really clever tools and methods, like counting rods and early approaches to calculations for astronomy.
Counting rods were especially interesting. People would use small sticks to represent numbers and perform calculations on a flat surface. It was like an ancient calculator, very visual and practical.
And with those rods, they could solve complex problems, from everyday trade calculations to more advanced work like astronomy. Observing the stars and predicting movements required precise numbers, and these tools made it possible.
Exactly. And then there were magic squares, which are arrangements of numbers in a grid where every row, column, and diagonal adds up to the same total. They were not just mathematical exercises, they had cultural and mystical significance as well.
I love that aspect. It shows that mathematics was integrated into both practical and symbolic life. People saw patterns, connected them to the universe, and found ways to represent harmony through numbers.
And what is remarkable is how systematic their methods were. Calculations for land, trade, and astronomy were done with incredible precision, long before modern tools existed.
Yes, and the influence lasted for centuries. Their innovations in arithmetic, geometric patterns, and observational methods laid the groundwork for more advanced mathematics in the region.
It is amazing to see how imagination, observation, and practical need came together in ancient China. Numbers were not abstract, they were tools for understanding the world.
And the combination of practical calculation and exploration of patterns like magic squares makes their mathematics feel alive, connected to both everyday life and the cosmos.
Truly. It reminds us that mathematical creativity has always been part of human culture, whether for survival, trade, or wonder at the stars.
And it shows that even simple tools, like counting rods, can open the door to incredible discoveries and ideas.
Sarah, have you ever thought about how much we owe to Islamic mathematicians from centuries ago?
Absolutely, Adam. One name that always comes up is al-Khwarizmi. He really transformed the way people approached calculations and problem solving.
Exactly. He wrote texts that introduced systematic methods for solving equations, which is essentially the foundation of algebra. But it was not just theory. These methods were applied to real-world problems like inheritance, trade, and land division.
I love that about his work. It was practical and accessible. People could use these ideas to manage everyday life, while at the same time, the concepts laid the foundation for future generations to build more abstract mathematics.
And did you know that his name is the origin of the term algorithm? The techniques he developed for performing calculations step by step became central to how people approached arithmetic and problem-solving across the world.
That is fascinating. It shows how mathematics can travel through time and cultures. A method developed in one place for practical needs ends up shaping the way humans think about computation centuries later.
Exactly. And his work inspired others in the Islamic world and beyond. Mathematicians continued to explore numbers, patterns and equations, expanding the reach of algebra and influencing Europe when these texts were translated.
I love imagining a scholar in Baghdad, centuries ago, carefully writing out these methods, thinking about how to solve real problems with clarity and logic.
And because of that, the concepts of algebra and algorithm became more than just abstract ideas. They became tools that could be applied, shared, and built upon.
It is amazing to see how curiosity, practicality, and careful thinking combine to create ideas that still influence us today.
Absolutely. Sarah, al-Khwarizmi and other Islamic mathematicians remind us that mathematics is not only about numbers, it is about problem solving, storytelling, and connecting ideas across time and space.
And it inspires us to think about the discoveries we make today. How might they shape the future, just as these ancient methods shaped ours?
Sarah, have you ever heard of Fibonacci and how he changed the way Europe thought about numbers?
Yes, Adam. He was the mathematician who introduced Arabic numerals to Europe. Before that, people were still using cumbersome counting methods that made calculations slow and difficult.
Exactly. With the Arabic numerals, calculations became far simpler. But Fibonacci is also famous for the sequence of numbers that bears his name.
I love the story behind that sequence. He discovered it while studying a problem about rabbit populations, how many pairs would be born over time if each pair produced another pair every cycle.
Right, and even though it started as a playful problem, the pattern he uncovered appears all over nature, from the arrangement of leaves on a stem to the spirals in shells.
It is amazing how a mathematical curiosity about rabbits turned into a discovery that connects numbers and the natural world.
And it shows the power of new numerical systems. Without the Arabic numerals, Fibonacci might not have been able to write down or explore these ideas so easily.
Exactly. It was a combination of a clever mind and a better way to represent numbers. That combination changed mathematics in Europe and laid the groundwork for future discoveries.
And the sequence itself continues to inspire. Artists, architects, and scientists have all noticed these patterns and applied them, consciously or unconsciously, in their work.
It is a beautiful reminder that mathematics can be both practical and poetic, connecting human curiosity with the rhythms of nature.
Absolutely. Fibonacci's work shows that even a simple question, like how rabbits multiply, can open doors to profound insights that endure for centuries.
And it encourages us to look for patterns around us, to ask questions, and to realize that even playful problems can lead to discoveries that change the way we see the world.
Sarah, have you ever thought about how mathematics and art came together during the Renaissance?
Yes, Adam. It is fascinating. Artists were not just painters, they were thinkers, using mathematics to create depth and realism in their work.
Exactly. The development of perspective was revolutionary. By understanding geometry and proportion, artists could make a flat canvas appear three-dimensional, giving viewers the illusion of space.
And it was not only about making paintings look real. It required careful observation and calculation. Artists like Leonardo da Vinci studied shapes, angles, and measurements to make everything line up perfectly.
Right. And during the same period, mathematicians were exploring probability. Gains of chance and gambling prompted them to think about likelihood and uncertainty in a systematic way for the first time.
I love that connection. The Renaissance was a time when curiosity about the world flourished, whether in art, mathematics, or science. People began asking not only how things look, but also how likely events are to happen.
And it shows how practical questions can lead to big ideas. Understanding perspective helped architects and artists, while thinking about probability laid the foundations for statistics and decision-making centuries later.
It is inspiring. Mathematics was no longer just about counting or trade. It became a way to understand beauty, chance, and the structure of the world itself.
And the dialogue between art and mathematics made both fields richer. Artists learned from mathematicians, and mathematicians found new ways to explore abstract ideas inspired by real-world problems.
Absolutely. The Renaissance reminds us that creativity and logic can work hand in hand, producing discoveries and works that continue to influence us today.
And it encourages us to see mathematics not just as numbers, but as a tool to explore, imagine, and make sense of the world in new and surprising ways. Sarah, have you ever thought about how René Descartes bridged the gap between algebra and geometry?
Yes, Adam. It is fascinating. Before Descartes, algebra and geometry were mostly separate. Geometry was about shapes and space, while algebra dealt with numbers and equations.
Exactly. Descartes had this brilliant insight that you could represent geometric shapes using algebraic expressions. It meant that curves and lines could be studied with equations, and equations could be visualized as shapes.
I love that idea. It is like giving numbers a form in space, turning abstract calculations into something you can see and reason about visually.
And it went the other way too. Geometric intuition could help solve algebraic problems. By looking at a curve or a line, mathematicians could understand relationships between quantities in a completely new way.
It really changed mathematics. Analytic geometry, as it came to be called, became a tool for everything from physics to engineering. It allowed for precise descriptions of motion, area, and space using a unified approach.
Right. Descartes' approach also emphasized the power of systematic thinking. By connecting two branches of mathematics, he opened the door to more advanced ideas like calculus and coordinate systems.
It is amazing to think that one insight seeing numbers and shapes as connected could transform the way humans approach problems and explore the world.
Absolutely. It reminds us that creativity in mathematics is often about making unexpected connections, finding links between things that seemed unrelated.
And Descartes' work shows how abstraction and visualization together can create a whole new way of understanding the universe.
Exactly. By seeing algebra in geometry and geometry in algebra, he gave mathematicians a powerful language to describe the world, a language we still use today. Sarah, have you ever thought about how Newton and Leibniz independently created something that would change mathematics forever?
Yes, Adam. Calculus is such a powerful tool, but it is even more fascinating when you think about the human story behind it. Both were trying to solve real problems in nature.
Exactly. Newton was looking at motion and the forces that govern the universe. He wanted to understand how planets move, how objects fall, and how change happens continuously.
And Leibniz approached it from a slightly different angle, focusing on the rules and notation that could make working with change and accumulation easier. His system made it easier for others to apply these ideas to problems in physics and engineering.
What I find amazing is that both of them, working separately, realized that you could break down complex changes into infinitely small steps and then add them up to understand the whole. It was revolutionary thinking.
And it shows the beauty of mathematics as a human endeavor. Curiosity, problem solving, and determination can lead to discoveries that reshape how we understand the world.
Absolutely. Calculus allowed humans to describe motion, growth, and change in a precise way for the first time. From falling apples to planetary orbits, it gave a language to the natural world.
And the story reminds us that great discoveries often arise from necessity. Newton and Leibniz were both solving pressing problems of their time, yet their insights became timeless.
Right. It is inspiring to think about the combination of observation, imagination, and rigorous thinking that led to such a profound leap.
And it encourages us to see mathematics as a living story, full of human effort and creativity, rather than just abstract formulas.
Exactly. Newton and Leibniz remind us that the greatest discoveries often begin with simple questions about the world around us.
And that those questions, pursued with curiosity and persistence, can change how generations understand the universe.
Sarah, have you ever thought about how much Euler shaped the way we write and understand mathematics today?
Absolutely, Adam. He was incredibly prolific, but what stands out is how he introduced clear and consistent notation that made mathematics much easier to communicate.
Exactly. Before Euler, mathematicians had their own ways of writing things, and it could get really confusing. Euler brought order, giving us notations that are still in use today.
And it wasn't just notation. He worked extensively with series, exploring patterns in numbers and infinite sums, finding relationships that were previously hidden.
Right. He had this ability to see connections between seemingly unrelated concepts. His work made complex ideas much more approachable and understandable.
I love that. Euler made mathematics readable, almost like a language. His notation allowed future mathematicians to build on his work without reinventing the wheel every time.
And his insights into series were remarkable. He looked at sequences of numbers and sums that stretch on forever, uncovering elegant patterns that still inspire research today.
It is amazing to think that one person could have such a lasting impact, shaping both how we write mathematics and how we think about it conceptually.
Exactly. Euler's work reminds us that clarity and creativity go hand in hand. By organizing ideas and exploring patterns, he transformed mathematics into a tool that is powerful and accessible.
And it encourages us to see notation not as a dull convention, but as a way to communicate ideas clearly, to connect minds across time and space.
Absolutely. Euler showed that the way we express ideas can be just as important as the ideas themselves, making mathematics a living, evolving conversation. Sarah, have you ever heard about Carl Friedrich Gauss and why people call him the Prince of Mathematicians?
Yes, Adam. Gauss was remarkable, especially in number theory. He had this incredible ability to see patterns in numbers that others could not.
Exactly. One story I love is from his childhood. He was asked to sum all the numbers from 1 to 100, and he came up with the answer almost instantly by spotting a clever pattern.
That is amazing. But beyond such tricks, Gauss really revolutionized the study of numbers, especially primes, and the way numbers relate to each other in modular systems.
Right. He explored modular arithmetic, which is about understanding numbers by their remainders when divided. It might sound abstract, but it turned out to be a powerful tool for uncovering hidden order among numbers.
And primes fascinated him endlessly. He studied their distribution and patterns, trying to understand how these fundamental building blocks of numbers were arranged.
What is inspiring is how he combined intuition with rigorous proof. He did not just guess patterns, he found ways to demonstrate them logically, setting a high standard for all mathematicians who followed.
Absolutely. Gauss' insights laid the foundation for modern number theory, cryptography, and even computer science centuries later.
And it all started with his curiosity, a playful mind, and the courage to explore numbers deeply, looking for structure where others saw chaos.
It is a beautiful reminder that mathematics is not just calculations. It is a way of seeing patterns, making connections, and uncovering the hidden harmony of the world.
Exactly. Gauss teaches us that even the most abstract ideas can be deeply human, driven by curiosity, creativity, and a desire to understand.
And that makes a story as much about the mind and imagination as it is about numbers themselves.
Sarah, have you ever thought about how probability and statistics got started?
Yes, Adam. It is fascinating. People like Pascal, Fermat, and later Bernoulli really laid the foundations for how we understand chance and uncertainty.
Exactly. It all began with questions about gambling and games of chance. Pascal and Fermat were corresponding about problems involving dice and cards, trying to figure out fair outcomes.
And from those playful questions, they developed systematic ways to think about probability. It was the first time anyone approached uncertainty with logic and calculation rather than just intuition.
Right. And then Bernoulli came along and expanded these ideas, thinking about larger sets of events, averages, and the way things behave over time. He helped formalize the idea that we can make predictions at randomness.
I love that. What started as a curiosity about gambling became a tool for understanding all kinds of phenomena, from population patterns to risk in daily life.
And it shows how practical problems can lead to deep insights. They were not just theorists, they were trying to solve real-world puzzles, and their work continues to guide us today.
Absolutely. Probability and statistics give us a way to make sense of uncertainty, to plan, predict, and understand trends, all because these mathematicians asked the right questions.
It is inspiring. Their work reminds us that curiosity, careful reasoning, and collaboration can turn simple questions into discoveries that shape centuries of thought.
And it makes us see mathematics not as abstract or dry, but as a living tool for interpreting the world and making decisions.
Exactly. Sarah. Pascal, Fermat, and Bernoulli show us that the study of chance is really a study of life itself, full of patterns, surprises, and insight. Sarah, have you ever thought about how mathematics changed in the 19th century?
Oh yes, Adam. That period was full of bold ideas that challenged everything mathematicians thought they knew.
Exactly. For instance, the development of non-Euclidean geometry completely reshaped the understanding of space. Mathematicians realized that the familiar rules of straight lines and parallel lines were not the only possibilities.
And that was revolutionary. It showed that mathematics could explore entirely new worlds of thought, not just the physical space we experience.
At the same time, imaginary numbers were becoming more accepted. Numbers that seemed impossible at first were now being used to solve real problems and describe new patterns.
And it opened the door to thinking abstractly about numbers, which eventually led to the beginnings of abstract algebra. Mathematicians were no longer confined to concrete quantities, they were exploring structures, rules, and relationships in a whole new way.
It is fascinating how these ideas built on each other. Questioning basic assumptions about geometry led to broader notions of number, and that, in turn, encouraged thinking about the underlying structures of mathematics itself.
Exactly. The 19th century was a period of expansion and imagination, showing that mathematics was not just a tool for calculation, but a universe of ideas waiting to be explored.
And it reminds us that challenging what seems obvious can lead to some of the most profound insights. New geometries, new numbers, and new structures transformed mathematics forever.
Absolutely. It is a period that celebrates curiosity and bold thinking, proving that mathematics grows when we dare to imagine beyond the familiar.
And it continues to inspire us today, showing that even abstract ideas, born in the minds of 19th century mathematicians, can shape how we understand the world. Sarah, have you ever heard of Bernhard Riemann and how he changed the way we think about numbers?
Yes, Adam. His work with complex numbers and the zeta function was groundbreaking, especially when it comes to understanding prime numbers.
Exactly. Riemann explored patterns that were hidden beneath the surface, using complex numbers as a tool to reveal the structure of the primes, which had fascinated mathematicians for centuries.
I love that. He was trying to see order in what seemed completely random. Prime numbers, which appear scattered among other numbers, suddenly had a rhythm when examined through his methods.
Right. And his ideas were not just about solving problems, but about creating a new lens to look at numbers, to see connections and relationships, that were invisible before.
It is fascinating how imagination and rigorous reasoning came together in his work. He was charting unknown territory, linking abstract ideas to the fundamental nature of numbers.
And the impact is still felt today. Mathematicians continue to explore Riemann's insights, trying to understand the deep patterns he glimpsed, which are connected to so many areas from prime numbers to modern physics.
It shows the power of human curiosity. One person asking questions about patterns and structures can open entire fields of study that endure for generations.
Absolutely. Riemann's work reminds us that even the most abstract mathematics has a story, a journey of discovery, and a human mind pushing the boundaries of knowledge.
And it encourages us to look at mysteries in our own world, to wonder, explore, and try to uncover the hidden order behind what seems chaotic.
Exactly. The beauty of Riemann's legacy is that it combines deep insight, bold imagination, and the timeless quest to understand the secrets of numbers. Sarah, have you ever thought about how Georg Cantor changed the way we understand infinity?
Yes, Adam. Cantor was truly revolutionary. Before him, infinity was more of a philosophical idea, but he turned it into a precise mathematical concept.
Exactly. He developed set theory, which is all about collections of objects, and used it to explore different sizes and types of infinity.
I love that. It is amazing to think that some infinities can be larger than others, and that he could rigorously prove it. That was something no one had imagined before.
And his work went even deeper. Set theory became the foundation for modern mathematics. It allowed mathematicians to define numbers, functions, and structures in a completely new way.
And it was not just abstract. By clarifying the concept of infinity, Cantor helped solve paradoxes and questions that had puzzled thinkers for centuries.
What is inspiring is his persistence. Many of his contemporaries resisted his ideas because they seemed so counterintuitive, yet he continued to explore and expand the theory.
It shows the courage of curiosity. Cantor saw possibilities where others saw contradictions, and that vision opened an entirely new branch of mathematics.
And today, set theory is everywhere, forming the language of mathematics, from basic arithmetic to advanced research in logic and beyond.
It is a reminder that bold ideas, even about something as abstract as infinity, can transform how humans think, reason, and explore the universe of numbers.
Exactly. Cantor teaches us that mathematics is a living story of imagination, rigor, and the courage to look beyond the obvious.
And it inspires us to ask bigger questions, to explore the unknown, and to see the infinite possibilities in the world around us.
Sarah, have you ever thought about how mathematics became the language of physics in the 19th century?
Absolutely, Adam. That was a time when people like Fourier and Laplace showed that mathematical tools could describe real-world phenomena with incredible precision.
Exactly. Fourier, for instance, studied heat and vibrations. He realized that complex patterns could be broken down into simpler, repeating waves, making it possible to understand and predict how systems behave.
And Laplace worked on celestial mechanics, trying to explain the motion of planets and the stability of the solar system. His mathematical methods allowed predictions with remarkable accuracy.
Right. What is fascinating is how they applied mathematics to real problems: heat, sound, motion, turning abstract equations into tools for understanding the physical world.
And it went beyond physics. Their methods inspired engineers and scientists in all fields, from electrical circuits to probability and statistics. Mathematics became a practical instrument for solving concrete problems.
I love that. It shows that applied mathematics is not just calculation, it is a way to see patterns, make predictions, and turn observation into understanding.
Exactly. The 19th century was a period when theory and application were intertwined. Mathematical insight led to technological innovation, and real-world problems pushed mathematics to develop further.
And it reminds us that the greatest discoveries often come from collaboration between imagination and practical need. Fourier and Laplace were both thinkers and problem solvers.
Absolutely. Their legacy shows that mathematics can describe the unseen forces of nature and give us a deeper understanding of the universe.
And it encourages us to see mathematics not as abstract numbers, but as a living language that explains the world around us.
Exactly, Adam. 19th century mathematics teaches us that curiosity, observation, and rigorous reasoning together can unlock the secrets of nature.
Sarah, the early 20th century was such an exciting time for mathematics and physics.
Absolutely, Adam. Mathematicians were setting ambitious goals, and physicists were exploring the universe in new ways. Hilbert's famous list of problems really captured the imagination of the mathematical world.
Right. Hilbert challenged mathematicians with 23 big questions, ranging from the foundations of geometry to number theory. They were puzzles meant to guide research for decades.
And what I find fascinating is how these abstract questions connected to the real world. At the same time, Einstein was using geometric ideas to describe gravity and the structure of space and time.
Exactly. He realized that the universe could be understood as a kind of geometry, where massive objects bend the fabric of space. Mathematics became the tool to describe reality itself.
And it shows the interplay between pure and applied mathematics. Hilbert pushed the limits of abstraction, while Einstein applied those ideas to explain phenomena that were previously mysterious.
I love that. It reminds us that mathematics is both a creative pursuit and a practical instrument. Ideas that begin on paper can end up describing the stars.
Absolutely. And the early 20th century highlights the human side of discovery, curiosity, ambition, and the desire to understand patterns, whether in numbers or in the cosmos.
It is inspiring. Hilbert's problems motivated generations of mathematicians, while Einstein's use of geometry transformed physics. Both show how deep thinking can reshape our understanding of the world.
And it encourages us to see mathematics not just as formulas, but as a storytelling tool, connecting abstract ideas to the very fabric of reality.
Exactly, Sarah. That period reminds us that bold questions and creative thinking can change the course of human knowledge forever. Sarah, have you ever thought about how modern mathematics expanded in the 20th century?
Yes, Adam. That period saw incredible developments in fields like topology and modern algebra, and one name that stands out is Emmy Noether.
Absolutely. Emmy Noether transformed algebra by focusing on structures and relationships rather than just individual numbers or equations. Her work laid the foundation for what we now call abstract algebra.
And topology was also gaining ground, exploring properties of shapes and spaces that remain unchanged under continuous transformation. It was a completely new way of thinking about geometry.
What is inspiring is how Noether's insights connected to both pure mathematics and physics. She showed that understanding symmetry in algebra could explain fundamental laws of nature.
Exactly. She worked on concepts that were highly abstract, yet they had profound implications for science, influencing how physicists think about conservation laws and symmetry in the universe.
And it was not just her ideas, but also her approach emphasizing deep structure, generalization, and logical clarity that influenced generations of mathematicians.
I love that. It reminds us that mathematics is not only about solving problems, but about discovering underlying patterns and relationships that unify diverse areas of thought.
Right. The combination of topology, modern algebra, and Noether's contributions shows how abstraction and creativity can lead to powerful insights.
And it encourages us to see mathematics as a living, evolving discipline, where even highly theoretical ideas can illuminate the world in unexpected ways.
Exactly. Sarah, Emmy Noether's legacy teaches us that bold thinking, clarity, and curiosity can redefine entire fields and inspire generations to come. Sarah, have you ever thought about how mathematics led to the birth of computer science?
Absolutely, Adam. It all started with discrete mathematics, the study of structures, patterns, and logic that can be counted or separated.
Right. And that field became essential when Alan Turing came along. He asked questions about what it means to compute something and how machines could, in principle, solve problems.
I love that story. Turing imagined a machine that could follow simple rules to perform calculations, which is essentially the foundation of modern computers.
Exactly. And earlier algorithms, those step-by-step procedures for solving problems, were at the heart of his thinking. They took abstract mathematics and turned it into instructions a machine could follow.
It is amazing how theoretical ideas in logic and discrete math became practical tools for designing hardware and software. Turing bridged the gap between thought and machine.
and the impact was enormous. From code breaking to computing machines, his ideas showed that complex tasks could be broken down into clear, logical steps.
I love that. It reminds us that computer science is deeply mathematical at its core. Algorithms and structures govern how computers work, yet they are also human inventions inspired by curiosity and reasoning.
Exactly. The early pioneers of computer science were both mathematicians and visionaries, imagining possibilities long before the technology existed.
And it encourages us to see computing not just as technology, but as a continuation of centuries of mathematical thought, creativity, and problem solving.
Absolutely. Sarah. Discrete mathematics and Turing's insights show that by thinking carefully about rules, logic, and patterns, humans can build machines that extend our intelligence in extraordinary ways. Sarah, have you ever been amazed by patterns that seem random but are actually deeply structured?
Absolutely, Adam. That is the world of chaos theory. At first glance, systems like weather, tides, or even population growth seem unpredictable, but beneath the surface, there is order.
Exactly. And fractals are a perfect example. These are shapes that repeat themselves at every scale. If you zoom in on a small piece, it looks similar to the whole.
I love that visual. It is like looking at a tree branch. The tiny twigs mimic the shape of the larger branch, and the larger branch echoes the shape of the entire tree.
And the Mandelbrot set is one of the most famous fractals. Its boundary is endlessly intricate, with patterns that never repeat exactly, yet there is harmony and structure everywhere you look.
It is mesmerizing. Even though the patterns are infinitely complex, the rules that generate them are surprisingly simple. It shows how simple processes can create astonishingly rich and beautiful structures.
And chaos theory teaches us small changes can have huge effects, like a butterfly causing a storm halfway across the world. It connects to fractals because both reveal hidden order in what seems unpredictable.
Exactly. It reminds us to look closely at patterns in nature, to notice repetition and variation, and to appreciate the subtle balance between randomness and order.
I love that. Fractals and chaos show that mathematics is not just abstract, it can describe the textures and rhythms of the world around us.
And it encourages us to see complexity not as disorder, but as an invitation to explore, observe, and discover the hidden beauty in every system.
Absolutely. Sarah. The Mandelbrot set and fractals remind us that the universe is full of patterns waiting to be noticed, and mathematics gives us the eyes to see them. Sarah, have you ever thought about how number theory, which once seemed purely theoretical, is now everywhere in modern technology?
Absolutely, Adam. One of the biggest applications is in cryptography. The patterns and properties of numbers help keep our digital communications secure.
Right. Concepts like prime numbers and modular arithmetic, which mathematicians studied for centuries just out of curiosity, are now at the heart of encrypting messages online.
And it is not just about keeping secrets. Number theory also plays a key role in coding theory, which ensures that information sent over networks, like text or videos, arrives accurately even if some data gets corrupted.
Exactly. Error-correcting codes rely on clever mathematical structures to detect and fix mistakes automatically. Without this, digital communication would be much less reliable.
I love how abstract ideas from centuries ago suddenly find a home in everyday life, from banking transactions to online shopping and secure messaging.
It is fascinating. Number theory has become both the shield and a guide, protecting data while making communication efficient and dependable.
And it shows the enduring power of mathematics. Even the most theoretical studies can become essential tools when technology catches up.
Absolutely. It reminds us that exploration and curiosity in mathematics can lead to discoveries that impact millions of lives in ways the original mathematicians could hardly imagine.
And it makes modern technology feel even more magical, knowing that deep patterns in numbers are keeping our world connected and secure.
Exactly. Sarah. Number theory teaches us that even the abstract can be profoundly practical, shaping the invisible infrastructure of our digital age. Sarah, have you ever thought about how computers changed the way mathematicians prove things?
Absolutely, Adam. One famous example is the four-color theorem. For over a century, mathematicians tried to prove it using traditional methods, but it resisted every attempt.
Right. The breakthrough came when computers were used to check thousands of possible cases. It was the first major theorem whose proof relied heavily on computation.
And that sparked a lot of debate. Some mathematicians wondered if a proof done by a machine could really be trusted, since no human could check every single step manually.
Exactly. But it also opened up new possibilities. Automated reasoning and computer-assisted proofs allow us to tackle problems that are simply too large or complex for humans alone.
And it shows how collaboration between human intuition and computational power can expand the horizons of mathematics. Computers can handle the heavy lifting, while humans provide insight and creativity.
I love that. It is not about replacing mathematicians, but enhancing their ability to explore vast problem spaces, discover patterns, and confirm conjectures.
And the four-color theorem was just the beginning. Today, computers assist in many areas of mathematics, from geometry to number theory, making proofs faster and more thorough.
It reminds us that mathematics is evolving. Technology allows us to ask bigger questions and find answers that would have been impossible before.
Absolutely. And it encourages us to see proofs not just as static statements, but as collaborative journeys between human reasoning and computational power.
Exactly. Sarah. The story of computer-assisted proofs shows that curiosity, logic, and technology together can push the boundaries of knowledge in ways we never imagined. Sarah, have you ever stopped to think about how wide-ranging Euler's influence in mathematics really was?
Absolutely, Adam. Euler was incredible. He seemed to touch every area of mathematics, from numbers and functions to geometry and infinite series.
Right. What fascinates me is how he connected these areas. For instance, his work with series revealed patterns in numbers that also influenced geometry and calculus.
And his notation made all of this accessible. By introducing clear ways to write functions, sums, and other concepts, he allowed generations of mathematicians to explore connections that were previously hidden.
Exactly. Euler had a unique ability to see links between seemingly unrelated topics, like how properties of numbers could inform shapes, or how infinite processes could be understood systematically.
I love that storytelling aspect. It is like he was mapping the entire landscape of mathematics, created pathways that others could follow and explore.
And it wasn't just abstract. His insights laid the groundwork for modern physics, engineering, and even number theory used today. Euler's work created bridges across disciplines.
It is inspiring to think that one mind could weave together so many threads, showing that mathematics is an interconnected tapestry rather than isolated puzzles.
Exactly. Euler teaches us that exploration, clarity, and curiosity can turn diverse ideas into a coherent vision, revealing patterns that endure for centuries.
And it encourages us to look for connections in our own work, to see how different ideas can illuminate each other in unexpected ways.
Absolutely, Sarah. Euler's legacy reminds us that mathematics is alive, full of relationships and stories waiting to be discovered and shared. Sarah, have you ever heard the story of Fermat's last theorem? It is one of the most famous puzzles in the history of mathematics.
Oh yes, Adam. Fermat scribbled in the margin of a book that he had a marvellous proof for an equation, but the margin was too small to contain it. That was over 3 centuries ago.
Exactly. For hundreds of years, mathematicians tried and failed to prove it. It became almost legendary, a challenge that captured the imagination of generations.
And then Andrew Wiles came along in the 20th century. He dedicated years of his life to this problem, working in secrecy, almost like a detective chasing a centuries-old mystery.
Right. Wiles used modern mathematics far beyond what Fermat could have imagined, connecting ideas from number theory, elliptic curves, and modular forms to finally crack the proof.
I love that. It shows how mathematics evolves. A problem posed in the 17th century required ideas developed over hundreds of years to solve.
And the story of Wiles' proof is almost as fascinating as the theorem itself. He initially found a gap in his argument, but he persisted, collaborating and refining his work until it was finally complete.
It is inspiring. Patience, creativity, and deep understanding were all essential. It reminds us that great discoveries often demand persistence over decades, even centuries.
Absolutely. Fermat's last theorem is more than just an equation. It is a tale of human curiosity, the evolution of mathematics, and the determination to solve what once seemed impossible.
And it encourages us to see problems not just as obstacles, but as invitations to explore, connect ideas, and push the boundaries of knowledge.
Exactly, Sarah. The theorem, Fermat, and Wiles together tell a story of imagination, intellect, and the enduring thrill of discovery. Sarah, have you noticed how mathematics continues to evolve even in the 21st century?
Absolutely, Adam. Prime numbers are still a hot topic. Mathematicians are uncovering larger primes than ever before, using computers and sophisticated algorithms.
Right. It is amazing how something as simple as a prime, numbers divisible only by themselves, and one can still hold so many mysteries and challenges.
And then there is the Riemann hypothesis, this century-old question that connects prime numbers to deep patterns. People are still attempting proofs, testing ideas, and finding new insights along the way.
What is fascinating is the blend of classical thought and modern technology. Researchers use centuries of theory alongside supercomputers to explore these patterns in ways that were unimaginable before.
I love that. It shows that mathematics is a living pursuit. Even today, questions from the past continue to inspire discovery and push the boundaries of knowledge.
And it reminds us that curiosity is timeless. Mathematicians are still chasing patterns, connections, and the hidden structure of numbers, just as people did hundreds of years ago.
Absolutely. It is inspiring to think that the frontier of mathematics is always moving, and each breakthrough opens doors to new questions and possibilities.
And it encourages all of us to see numbers not just as abstract objects, but as a rich landscape full of secrets waiting to be uncovered.
Exactly, Adam. The study of primes and the ongoing attempts at the Riemann hypothesis show that mathematics is both timeless and ever-changing, a true adventure for the human mind.
Sarah, it is fascinating how mathematics has moved beyond pure theory and is now shaping fields like biology, economics, and even machine learning.
Absolutely, Adam. In biology, for example, mathematics helps us model everything from population growth to the spread of diseases, giving insights that are impossible to see with observation alone.
Right. Equations and models can predict patterns in ecosystems, track epidemics, and even help design effective medical treatments. It turns raw data into actionable understanding.
And in economics, mathematics is at the heart of understanding markets, predicting trends, and evaluating risk. It allows economists to create models that simulate complex financial systems.
Exactly. Without mathematical modelling, decision-making in finance and policy would be far less precise. It gives a way to quantify uncertainty and make informed choices.
And then there is machine learning, where mathematics is literally powering artificial intelligence. Algorithms identify patterns, make predictions, and improve themselves over time.
I love that. Machine learning combines statistics, optimization, and data analysis to create systems that can learn from experience, a modern manifestation of centuries of mathematical thinking.
It is incredible how mathematics acts as a bridge, connecting abstract ideas to real-world applications that impact health, wealth, and technology.
And it reminds us that mathematics is not confined to classrooms or textbooks. It is a living tool that explains the world and allows humans to shape it.
Absolutely. Whether predicting the next trend in a market, tracking the spread of a virus, or teaching a machine to recognize images, mathematics continues to be an essential companion in discovery and innovation.
Exactly, Sarah. It is a story of human ingenuity, showing that patterns and logic can illuminate complex systems and transform our understanding of life itself. Sarah, I came across the work of Surajit Ghosh and I thought we should talk about it. He claims to have offered what he calls elementary proofs of the Riemann hypothesis.
That is intriguing, Adam. The Riemann hypothesis is one of the most famous open problems in mathematics, and many have tried to crack it. So Ghosh's claim is certainly bold.
Yes, and his approach is interesting. According to his article, the idea is to introduce a kind of delta function similar to the gamma and pi functions. We define certain poles and zeros of the zeta function, and then argue that all non-trivial zeros must lie on the so-called critical line.
I see. So in narrative terms, Hugh is attempting to simplify or elementarize methods that have traditionally been quite deep and complex. That's a courageous goal.
Exactly. He presents 3 different proofs in his paper, including one via that delta function idea, and others via more algebraic manipulations.
But as always with such claims, the important questions are how those proofs stand up to peer review and how the broader mathematical community assesses them. Do we have wide acceptance of his result?
That's where things get more cautious. I've found that the paper appears in an open access journal that may not have the highest level of scrutiny. Also, others in the field have flagged the claim as unverified. For example, a Reddit thread mentions his name and raises doubts.
That means his work is part of the larger story of attempts at the hypothesis not yet a universally accepted proof. It reminds us how in mathematics even a plausible-sounding approach still needs rigorous validation.
Right. But I do find it inspiring that someone takes up such a monumental change. It shows the ongoing vitality of mathematical research, where people continue to bring fresh ideas to long-standing problems.
Absolutely. Even if a claim eventually doesn't hold up, the exploration often yields valuable insights or new techniques that others can build on. So Ghosh's work, regardless of its final status, contributes to the culture of inquiry.
And for listeners, we might say this mathematics isn't just about what is currently proven, but about ideas, attempts, risks, and the community's collective judgment over time. Ghosh's story is a reminder of that.
Exactly. So while we remain open and curious about his claim, we also recognise that the path to acceptance in mathematics is rigorous and collaborative.
Well said, Sarah. And perhaps listeners will be inspired to follow the story themselves, to learn about the zeta function, prime numbers, and to understand how a claim like this is evaluated over time.
Indeed. Mathematics is a human adventure as much as a logical one, and these ongoing efforts remind us of that.
Thanks, Sarah. I'll keep an eye on how the community responds to Ghosh's work, and maybe we'll revisit it if it progresses.
Sounds like a plan. Until next time.
Sarah, after all our discussions, I keep thinking about the incredible journey of mathematics from simple counting sticks to the abstract theories we explore today.
Absolutely, Adam. It is amazing how humans started with tally marks and pebbles just to keep track of positions, and now we are probing the deepest structures of numbers, shapes, and even the universe itself.
Right. Along the way, we saw civilizations like Egypt and Mesopotamia using math for practical purposes, Greek and Indian mathematicians exploring patterns and concepts, and the modern era pushing abstraction, computation, and applications everywhere.
And it is not just about numbers or shapes anymore. Mathematics now drives biology, economics, physics, technology, and even artificial intelligence. It is the language that connects ideas across disciplines.
I love that perspective. Each era added layers notation, proofs, abstraction, computational tools, and built bridges to new ways of thinking. It is like a human story written in logic and imagination.
Exactly. And the beauty is that this journey is far from over. With emerging fields like quantum computing, data science, and complex systems, mathematics continues to evolve and surprise us.
It reminds us that curiosity is timeless. Just as ancient humans wondered about numbers, modern mathematicians explore the frontiers of infinity, symmetry, and patterns yet to be discovered.
And it inspires everyone listening to see mathematics as more than formulas, an adventure of the mind, a tool for understanding, and a way to glimpse the future.
Absolutely, Sarah. From counting sticks to exploring the cosmos through abstraction, the story of mathematics is a testament to human creativity and the endless pursuit of knowledge.
And who knows, Adam, maybe the next breakthrough is waiting for someone listening to this very conversation, ready to add the next chapter to this incredible journey.
Exactly. Mathematics is alive, ever evolving, and always inviting us to explore further.